All right. So why don't we get started? All right. So I gather the TAs are working on the tests, and they will let us know as soon as possible. The runtime is now in, well, you've seen the releases. It's now at the point where a program should link. There are a few various missing, and actually you can call print now, but or py print, but not much, and a few other things you'll have to. So if you can cons up a string or an integer on your own, well, yeah, make int also works. So you can do a few very simple things, and that should be completed. The rest of it should be completed pretty soon. Now I hope you've had a chance to look at it at least, because even in its current state, it gives you basically everything you're going to need to know. There are probably a few details that I have neglected to properly document that we'll have to get into, but other than that, everything should be fine. Okay, so again, so what I suggest is that you, in your groups, that you plan a strategy that has some chance of getting things working in layers, if you will, or in stages, so that you're not in the situation of coming up to the last minute with nothing that works. I mean, that just isn't good. So once you get, say, a simple print statement to work, printing an integer or something like that, then you can do all of the stuff. At that point, you can do all of the stuff that involves if statements and so forth, so you can get that working. And then you can get ordinary function calls, you can get method calls, and so forth. So again, be very cautious that you have found that you understand what things are supposed to be done for you in the runtime, because if you don't, you will spend an inordinate amount of time duplicating the effort. I can do it quickly. You can't, probably. Well, maybe some of you can, and if there are any of you who can, then I'd like to speak to you, but I have various uses that we could put you to. But so it's probably better to leave that to me, and so make sure that you aren't doing that. Now, some of you may be disappointed with the fact that we aren't doing garbage collection, which means that you're leaving crud all over memory as you go along every time you create a tuple or something like that. Well, if you want to do garbage collection, you can. I can take that as an alternative extra credit thing. Not sure I'd recommend it, because the only kind you're going to get working is conservative garbage collection. But if you're feeling adventurous, we can work something out. Talk to me first, however. It's not for the faint-hearted. Okay. Good. Questions? Issues? All right. We were here, or very close to here, and I was talking about the problem of how do we access non-local variables that are inside a function but are not local to the function you're currently executing. As, for example, here, where we're accessing the variable x1 inside f3, even though that's defined way out there in f1. So the trick here was to do this sequence in which we follow the links, the static links, just as you follow the links in an environment diagram, and get the value. Now, in our system, actually, so in this slide, I'm assuming that we pass the static link as a parameter, as an explicit parameter. That gets kind of confusing, so I sort of prefer the GNU way, which is the way we'll do it. And that works like this. It's just a different convention, nothing else. It's just a different convention. They reserve a register, or they use a register, I should say, a general purpose register, ECX, to pass the static link. So what happens is that the function f3, when we call f3, say right here, for example, down there at the bottom, we pass to F3 whatever the static link is that F3 is expecting. So in this case, since F3 is defined inside F2, the static link that we pass is F2's frame. And since this is F2 that's doing the calling, it knows what its frame is. It's just its base pointer, so it just passes that in and calls F3. If F3 had been defined instead inside F1 and F2 was then calling it, what would F2 do first? Where would it get ECX? Well, maybe we should go through the rest of this slide first. So, F3 now, assuming it's going to need, if it needs the static link for something, can save it as a local variable. So the way that works is local variables on the IA32 are negative relative to the base pointer. So it saves it as a local variable. And for convenience, we keep it we always put it at the same location, the static link at the same location, -4 in this case, just so that you don't have to do any thinking about tracing them back. And then when F3 needs to access X1, it simply does the same code as before, except that first of all, it pulls that static link from this local variable and then follows it back. And second of all, since we're passing the static link in a register instead of on the stack, we can use a different instruction. We no longer have to skip that implicit first parameter. So X1 is now at 8 off the frame pointer, off F1's frame pointer instead of 12. So this is the convention that we'll be using here. So again, let me ask this question. Suppose that F3, instead of being embedded inside F2, suppose F3 had been above F2. It had been defined inside F1. And now I'm in F2 and I want to call F3. Where do I get the ECX? Where do I get the value of the static link in that case? How do I get the value of the static link when I'm inside F2 calling F3, assuming that F3 is out there inside F1? Right, this is indicating a large degree of sleep deprivation, which is not good. Okay, what do you think? So it would still be an ECX. Well, we'll assume. All right, wait. We'll assume that F3 does its call somewhere in the middle. So you can't necessarily depend on ECX not having been changed in the interim. All right. How about you had something? Yeah, go ahead. Uh-huh.
So you can either do it as a linker, you can do it as an runtime, absolute address, or you can do it as offset F2,
Well, no, wait a minute. No, we're not talking about the code address. We're talking about the static link. So the compiler knows that F3, in this alternative scenario where F3 is defined immediately inside F1 instead of inside F2. Compiler knows where its nesting is, and it knows what its code address is. So the only question is, where does it get the ECX value? What value of ECX? Instead of this instruction here, moveL EBP to ECX, what does it have instead? Where is it going to get that static link? It's important to understand this, I think. Otherwise you don't quite see what's going on here. All right, what do you think? How will you do that?
F2 knows what F1's right, so pass it.
Well, here is F1, here is F2 passing its base pointer when F3 is buried inside it. What does it do when F3 is inside F1?
F2 has a static link to F1.
Right.
Pass that into
And where is that static link?
-4 EBP.
That's right. So we'd simply change this to -4 EBP to ECX, because in this case, the static link that we're supposed to pass to F3, if F3 is immediately inside F1, is supposed to be F1's frame pointer. F1's frame pointer is the static link that it passed to F2, therefore, or that something passed to F2, I should say. Therefore, we use that static link. By the way, that's the same answer that you'd get here for this call. Nope, no, it isn't. I'm sorry. This F2 of 9 is I see. That was just the call inside F1. So in this case here, F2 of 9. So this is a call inside F1 to F2. What gets passed as the static link? What gets sent into ECX? Yeah. That's right. It would just be F1's base pointer. Okay. It's important that you, if this discussion is confusing, then by all means ask your TAs, or as necessary, understand it, because it's sort of useful to until you can answer those questions, you don't quite understand the representation here, and so it's important to do that. Okay, good. So let's go on here. Well, now suppose that we don't know who's nested inside what. We're just given this function parameter, this function value, and we want to call that. So we have a function called caller that you pass it a function f, and it calls f. Right? Oh dear. Oh, I haven't updated this. I'm sorry. My mistake. Now in this, for this class, for this particular offering of the course where this slide got made up, we were doing something a little bit different. We were passing function parameters in. They would be two slots, two parameter slots. So that was kind of annoying. But here's what would happen if you actually pushed both. If you actually had, the idea is basically this. We take the static link, we pull out the static link. The thing that we pass, the function value f, will contain two things. It'll contain a static link, and it will contain a code address. So we'd simply push, or as in the GNU, I'll have to update this for GNU again. We'll simply push the static link, pull the static link out of that function value, push that, or pass it as the static link parameter, and then we pull the code pointer out of the function value and call that. I think this slide is probably, this definitely has to be resolved. It has to be revised so that it's a bit less confusing, since it's using an old parameter passing convention. Okay, so this is that's all you really need to know about this. Wherever the function value is, wherever we point it, and in our case it's just going to be a pointer to something, you pull the appropriate values out of it and call the function. I'll update it so that this looks like what you should do in the project, and I'm sure that'll be helpful. So, and the point here is that we could do the same thing with all functions. In other words, every time you see F3 So every time we have a new function, like, as for example here, what you could do is for each one of these definitions, F1, F2, and F3, you could build at the time that you enter F1, you could build a little variable, a little thing on the stack containing a static link, namely your own base pointer and the code pointer for F3, and then every time you want to call it, you could just refer to that thing and just use the same code for calling function-valued parameters as you do for calling named functions. But we don't usually do that in practice because it does slow things down a bit. So this is the code here again, which needs to be. In fact, I should probably update all of these to be sure. All right. So I don't think we've already done enough of this. That I think at this point I should just continue. Okay. Now again, the fact that GCC uses this interesting convention with ECX has certain advantages. It means, for example, that if you call a function at the outer level, you can just ignore passing. You know that it's not going to need a frame pointer, so you can do nothing. You don't have to worry about that at all. And furthermore, if you happen to be a function that doesn't have anybody nested inside you, then you also know, well, that doesn't call. I'm sorry. If you happen to be a function that doesn't call anybody that's nested, you can also ignore your static link, and that's kind of, both of those are kind of advantages. And I just wanted to make this comment that the way that we've been doing an obvious way of handling parameters, and it goes along with having a stack machine, is that every time that you want to pass a parameter, you just push it. And then when you're done, you simply pop those things back off the stack. So, for example, here we can pass two parameters to say a parameter 2 and some value 8 to a function called g. This is another holdover from a previous year. This one, in this one, we were passing I think we passed the number of parameters or something like that. Anyway, we could do exactly. We could do the same thing. So we take a value, we add 2 to it, we push the result, we call g, and then when we're done, when we come back from g, we pop the value back off the stack. So that's one way to do it. Perfectly okay. But another way of doing the same thing is to move the stack pointer ahead of time. So right here, sub L4 off ESP, is to just reserve all the space you need ahead of time for the parameter list, then stick things into that parameter list, and then call G. And in fact, you could unreserve the space or not as you see fit. Either way, in any case, either way works perfectly well. You'll find that the GNU compiler does not tend to push things. It tends to reserve some space on the stack and then stick stuff into it. As long as you achieve the same effect, it doesn't really matter. All right. And you'll also find, when you review some code, if you review some code, especially it's different on the Mac actually, you will occasionally see GCC doing these mysterious things with the stack pointer, like anding in a funny value. What it's doing is it's complying with some convention for that particular machine that says that the stack is always expected to be aligned in a certain fashion. In other words, always aligned on a 4-byte boundary or on an 8-byte boundary or a 16-byte boundary even inside. I think on the Mac it's 16 bytes. And for reasons that have to do with not exactly sure what, but the only time that's important is when you're calling a system call and it expects it. But you will occasionally see mysterious things like that, and there's nothing conceptually difficult going on. It's just a funny little thing. All right, so we've handled basically what we've been doing. Every time you push something on the stack, you're actually making a copy of it. So you're pushing a copy of the value onto the stack. And this is the type of parameter passing that's used universally in C, Java, and Python. You will occasionally see ignorant people, as it says here, that really annoy me, as you can tell from the tone of that red text, who refer to what Java does as passing by reference, because you pass a pointer to something, and therefore you can modify it. Well, that's not what pass by reference means. If it were, then we would not say that you pass integers by value. You'd say you'd pass them by integer, which makes no sense. So, what this does now, a reference parameter, a true reference parameter, which you have in C++ and Pascal, it means basically that if you do an assignment, x equals y, inside the body of the function, that affects the value of the parameter, that affects what the value of the actual parameter that you passed. So in other words, here I'll just put it, if we have any chalk. Pass by reference means that if I have a function f of, say, x, and I set x to 42 inside the function, then if x were being passed by reference, that means that when I call it out here with some value y, that afterwards y would be equal to 42. And of course that's not what happens in C, and it doesn't happen in C if this is an int star. Now, int star x, x gets null. That does not cause y to be equal to null when you come out of the function, when you come out of it. This is something that many of you probably encountered in learning Java or C. You kept expecting. In fact, I know because I asked this on tests in 61B, and people get it wrong. You assume that assigning to a pointer parameter will change the pointer. No, it doesn't. So this is called. So this phenomenon here is all passed by reference. And in C++, however, you can do this: int x, int ampersand x, and now x equals 42 will in fact do the right thing. It will set the parameter y down here to 42. That's passed by reference. But what C and Java and Python do, that is passed by value. It is exclusively passed by value. It is nothing else than passed by value. All right, enough. I've had my say, and boy, that feels good. I look forward to this lecture in every single class because all right. So, but this is simple. I mean, so this is a new feature. It's been around for a while, and it's really simple. All you have to do is pass the address of the parameter, and at the receiving end, your compiler has to know that it's receiving an address, so that it should be assigning through the address rather than the usual thing. Okay. So there's not really anything particularly interesting here, but we can have variations on this. So in some languages, Ada is one, actually Fortran also have a rule in which they say, well, we're not quite going to do this. We're going to, what instead we're going to do is we'll pass the thing in by value. But if you change it, we'll, inside, we will, when you leave, we will copy it back out to where it came from. So while you're executing, you won't change the actual parameter while you're executing, but when you're done, it will be changed. And there are various reasons for this, having to do with avoiding indirection and all that sort of business. So it's a little bit tricky to do this because of this case, f of a sub k. Because as you might imagine, k, who knows where k comes from? If it's a global variable, it might be changed while f is operating. So f could be sort of sneaky and change k. And what's supposed to happen is that the value gets put back where it came from, which means basically that in order to implement copy in, copy out in this case, what the implementation will do is it will compute the address of a sub k at the beginning, copy from there, and then it will save that address in some safe place and assign back to it when you come back. So here's this little question down here. Hint. You know, I'm not going to ask you to answer this question right now. I'm just going to put this question up, and you can speculate to yourself, you know, that really has the form of a test question. I wonder. Yeah, who knows? Well, Hilfinger never tells us what's going to be on the test, but I wonder if this is a hint. I don't know. All right. And now we come to everyone's favorite, call by name. Now this has a very interesting history. When Algol 60 has a particularly elegant, it has probably still the nicest language description you'll find. And the authors were striving towards simplicity. And they took a misstep as a result at one point. They said, how are we going to define the effect of a call? Wait, I've got it. We'll simply say that when you do a call, it is as if you called the procedure and substituted the text of the parameter for inside the body of the procedure. It's as if you did a sort of a dynamic inline expansion of the procedure. So calling f of x, when we call f of a var, it becomes a var gets 42. And we have to make some provisions because there might be name clashes. You know, there might be local variables inside f that just happen to be the same as the variable name outside. So we'll just pretend there's a little renaming that goes on, but otherwise we'll stick to this model. So they said that, you know, they just wrote the spec. This was obviously in advance of any implementations of Algol 60. They wrote this spec. They said, boy, that's nice and simple. That's easy to understand. But it had some rather interesting consequences, which are exemplified by this thing called Jensen's device, so-called because Jensen noticed that this mechanism, which came to be called call by name, was extremely powerful. Here's his device. He imagines this procedure, we'll call it do it, and it takes a bunch of parameters, I, L, U, X, X0, E, and all it does, look at this loop. It looks perfectly harmless. We set X to X0, the initial value, and we step the variable I from, and I is not, there's no, 4 does not define a new scope, so that I there is the same as the parameter I. For I gets L until U, step by 1, we simply set X to E, and so it looks like what you're doing is you're setting X to E, U minus L plus 1 times. Okay, sounds very nice, except that that's not really what happens. So we look at, for example, this procedure here. Do it K1n. Substitute in all of those procedures, do the substitution, and what you have is a loop that sums the values of A into Y. So it does a reduce, basically, of A by Y. Because Y plus AK, not the value of Y plus AK, but Y plus AK, the expression, gets substituted for E right there. And then you have, this is harmonic numbers. For those of you who know what harmonic numbers are, they're sort of the sum of, the series is the sum of 1 over n, for n goes from 1 to whatever. And so here you are. It's kind of weird. And of course, the immediate question is, what on earth can you do? How on earth can this work? I mean, this is terrible. And indeed, it means that it made Algol 60 implementations rather slow in some cases, at least for doing anything when you had a parameter. They introduced a by value. You could say that parameters were passed by value, and it would pass them by value. I don't know whether they did that realizing what they had done later on or not, but in any case, they did that. So the question, of course, is how do you make it work? And the answer is actually pretty simple. We just you just have to put in functions invisibly. All right. So we put in these functions. They took the name thunk. It's not clear where that word comes from. Some people think that it's sort of the what is it, past participle of think. Or something. Some people think that it's the sound of a stack pointer hitting the bottom of the stack. We don't know. Anyway, they're called thunks, and the idea is that we will simply translate anything that looks like that into a bunch of lambdas. This, of course, is not valid any language. It's sort of made up here on the fly. We'll simply pass in all of these parameters like k, 1, n, and so forth as addresses, as functions that compute addresses. And in particular, they have the functions take no parameters. You just call them and they return an address. And then as a result, you can. So for this one, the one that's tricky is the one where you compute the address of where you do have an expression like this, in which case you have to have some sort of temporary variable, and you pass in the address of that variable. It gets kind of tricky. So that's right. So that's what they did. That was basically the implementation, or something like that. They can also do, there are a few other things you can do to maybe speed it up a little bit. But let's just say that in later languages, despite the fact that this has the attractive property that you can do Jensen's device, they decided maybe this is going just a little bit too far to get output parameters. And so they took two routes. Either they took the route of having parameter mechanisms like copy in, copy out, or by reference, or they said, we'll just have call by value. And that's what C did, just have call by value, and everything is fine. Okay, so there you are, a quick whirlwind tour of the rest of the details in doing function implementation. Now, I'm going to spend the rest of the lecture, after take a brief break, I'm going to spend the rest of the lecture explaining something that I noticed I did some disordering of the lectures this time, so that your homework mentions some stuff that we haven't talked about yet. So I thought it would probably be a good idea to talk about it well in advance of the homework being due. So I'll do that next. But first, questions about any of this? Been standing here talking for too long. Okay, fine. Well, let's take a brief break. Yeah.
For project 3, for the intermediate language,
Mm-hmm.
we can either use a stack machine or the 3-coder. We can either
Intermediate, there's no intermediate, you don't have to use any intermediate language if you don't want to.
I was thinking because we wanted to split up the work, so it's probably easier to do it that way.
Okay.
But do you think stack machine is probably a lot easier than 3-coder?
Well, let's think about what you'll, it depends on what you want to do. If you want to save up intermediate language into some vector and then generate code from it, then it doesn't really matter what you do. If you want to generate code immediately, you probably want to use a stack machine because you don't have to worry about register allocation. The registers might be a little easier to deal with in that case. I mean, that's just sort of off the top of my head. Because then what will happen is that you have calls. You make a call to, your code generator makes a call to something as if you could emit stack machine stuff. And the implementation of the stack machine is generate IA32.
Then we can split up the work like that.
That's right. That allows you to split up the work. But I mean, either way allows you to split up the work. It's just that there might be some extra complications if you're. You might want to do. Well, I don't know. You could probably get away with. You could probably do immediate generation from 3 address code as well. You want to be careful about a few things when you. Well, with registers, the trick is that you want to be able to issue instructions and at the same time say, oh, by the way, this is going to be the last use of this variable. So otherwise you'll have a lot of awful spilling. But if for example your code is generate a compiler temporary, put something into it, generate a compiler temporary, put something into it, then do something with those compiler temporaries and you're done with them. If that's your translation, then of course at that point, the code generator, the guy who's calling this thing, generating the 3 address code, know at that point that you're not going to use this register again. That was the only use of it. You can say that, and that's helpful for doing register allocation.
I will think about it.
You'll find out when you do this, I'm sure. Yes.
Okay, thank you.
Yeah. All right. Why don't we get started again? So this is actually a special effect we haven't talked about. How are we going to deal with sequences of things? Well, I mean, I'm sure you can figure this out on your own, but the obvious thing to do is to say, well, assuming that we've laid memory out, assuming that we've laid this sequence out in a vector of memory in the usual way, we can figure out where everything must be. Let's suppose that, let's imagine that we have this array X, or in Python, a list, or tuple. And let's just designate, use ampersand, we use abuse notation, say ampersand X is the address of the beginning of that, the first element of that array. Then it's easy to do the computation. You simply say, well, okay, since indexing begins at 0 in C, we just take the index, we multiply by the size of each element, which we'll call S for the stride, and that's the address. We add that to X, and that's the address. Now, it's mind you, this is not this is an address, just a plain number, not a C pointer. If it were a C pointer, then there would be it would do the wrong thing. It would throw in an extra multiplication. So here this is not really C code, even though it looks like C code. This is the address of X plus that number. That, by the way, is another pet peeve. They keep calling this address arithmetic in C++ or C, even though you're not really adding integers. It does some extra stuff first, like multiply the integer by some stride value. Okay, well now this is one of an example. This is called what we call the access algorithm for this array, for array access. And in intermediate code, you'd do something like this. You'd first of all compute the address of A, put that into a temporary. You'd compute the value of the expression A sub E. You'd compute the value of the expression. You'd put that into a register, and then you generate the code. Arrow here means generate code. Generate the code that sets that multiplies by the stride, and then you generate the code that adds that to the address of the array, and that's it. You now return. The result is you have put the value of the element that you're after into T0, and at that point the program would then dereference T0 or something like that in order to get at the value, whatever it was supposed to be doing. You can use, this same thing will work both for the left side and the right side. You just, in the case of the left side, you fetch from that address. In the case of the right side, you store into that address. So now, what about higher dimensional arrays? Well, actually, we've now answered the question, because a higher dimensional array, like a 2D array, is just an array of a 1D array of 1D arrays. Now, you can do this in the manner that Java does it, where you implement this by, when you go beyond one dimension, you have you actually make that since an array is a pointer to a bunch of, or an array pointer is a pointer to a vector. You simply have a 2D array be an array of pointers to vectors, and that works. The general term for that is actually ILIF vector, but it's not necessarily great when you're doing some hardcore array processing on a GPU perhaps, or something like this, where you'd sort of like the memory to be more gathered together, more contiguous. And there are various things you can do if the memory is contiguous. So we can pack all of those elements. So instead, we can pack all of those elements together, and that gives us so that we have an array of rows, and that's it. We can use exactly the same formula. So Aij looks the same, except that the computation, we first add I times S times N, where N is the number of columns. And that gives us, that's the size of each, that will be the size of each row of is the size of each row of the array. So we take the number, since I is the index, which row we're on, we multiply that by S times N, the size of the row. And that gives us the beginning of the appropriate row. And then we just add J times the one-dimensional stride, and that gives us the element in the row. So this is just actually two applications of the same one-dimensional algorithm. Fortran, for reasons that I don't know, actually, I keep meaning to ask somebody about this, and I haven't quite gotten around it, decided to do things differently. So in Fortran, it's not, instead of being a vector of rows, it's a vector of columns. So you have to reverse the roles of I and J in that case. And it's kind of, I don't know why they did that, but they did. Right. So that's pretty neat, pretty straightforward. Here's the intermediate code that you generate. So you compute you need the value of the size of the row, which may or may not be constant depending on your language, and then you just do all of this computation and you get the final answer. Pretty straightforward. Well, this is interesting. But since the algorithm is the same, it might occur to you that maybe we can do some refactoring. Maybe we can package all of this up. And this leads to the idea of the array descriptor, or fat pointer of some kind, sometimes called fat pointer, that looks like this. It's, instead of being an ordinary pointer, this thing contains all the information you need to access an element of an array. So you look at the form of the computation up there. We have something, some constant or some link time constant anyway, plus a product of the first dimension E2 times some number plus the second dimension times some number. So all we have to do is store S1 and S2 and VO there, which is short for virtual origin. And then our algorithm is very simple. You simply take this guy, you multiply the first index by this guy, and you multiply the second index by that guy, and you add them all together, and you're done. So that we've sort of encapsulated everything. And then the trick is just to make sure you set it up by putting the right values into this descriptor, and everything works. That's the size of a row, right? So we can do all the blah, blah, blah. You can do the code that might be interesting to you. But the interesting thing here, what this allows us to do is to do some clever tricks, which I also ask you to do in the homework. So for example, if we start the indices at 1 instead of 0, then we have to be careful to subtract 1 from each of the indices before adding the stride. Or we can do some algebra and reorganize everything back into the original form for an array vector, so that the virtual origin is now the virtual address of E00, which you get by subtracting S1 times S1 and S2 from the address of the first element of the vector. And now the algorithm is the same. We don't have to do any of that subtraction anymore. The algorithm is the same if you use the elements of the array descriptor. And the interesting thing, and what I ask you to do in the homework, are some other manipulations. You can even do cute things like transpose the matrix with an appropriate array descriptor. So it's kind of interesting. All right, so that's arrays, and we will continue. I'll see you on Wednesday.